We're going to take a look at how we do powers of complex numbers, and that will lead on to the idea of also finding the roots of complex numbers. But before we go ahead and do that, let's just quickly review the properties that we already know about complex numbers, especially using the polar form. So here in your textbook you can see the properties of using the polar form, known as the cis theta form. Just remember that when you multiply two complex numbers, you add the arguments, and if you divide, you subtract the arguments. Now this last property here is just mentioning that you can write a complex number with additional cycles added to the angle here. So more about this later when we actually do the roots of complex numbers. This proof here shown, and by the way this is on page 381, is important to have a look at. So I'll just briefly talk about it, and you can spend your own time to have a look at it in more detail. So to prove that the cis of theta times cis of phi actually will equal the sum of those two angles there, we can use the compound angle formula. So when you expand it, okay, remember this is how you write cis in the long way, and then you multiply those terms, you'll get all the real parts here. If you identify this carefully, you'll see there's two causes and there's two sines here. So I'm just going to quickly go to the formula sheet and have that side by side. Okay, so you scroll to the trigonometry section, you can see there's a formula. Gotta go to the HL section with the two cos expressions together and then the sine. And what we're asking for, just zoom that in a bit, okay, and minus sine, so that means we're doing cos of a plus b. And this one has the mix product, and it's also a plus, so you want sine of a plus b, okay? So the first bit's cos of a plus b, and the second one's sine of a plus b, and that's what they've written there. And then you compact those two expressions back together in cis form. So that's a really nice proof using the compound angle identity. You can do something similar here with division. So why are they multiplying by negative phi? Cis of negative phi is actually the conjugate of the complex number. Okay, so remember when you divide by complex numbers, typically you will have to rationalize that denominator, so you do it by multiplying by the conjugate over the conjugate. Okay, and then you already know that phi plus negative phi will be 0, so we can use the previous result as a known fact, leaving you with cis theta minus phi. So that's a really good result. Okay, so let's go back to this set of properties, and if you keep going further down, they just reiterate multiplying complex numbers. Okay, you multiply the modulus and you also add the argument. So this is just the introduction of modulus. Okay, in the previous part they didn't talk about it. We keep going and it'll lead on to the Euler form, and we already had a look at this as well. You can use Euler form to multiply complex numbers just like you were doing with indices. Let's talk about de Moivre's theorem. Okay, de Moivre was a French mathematician and found this particular observation with complex numbers. Basically, this is what we're going to look at. More importantly, you can see that n can be a rational number. Okay, doesn't just work for whole number powers. So that will lead on to the idea of taking roots of complex numbers, which is the final thing you'll learn in this whole section. If you observe this information they've written here, you know, figure out what z squared is, get that result there, work out what z cubed is, and you notice how they use z squared's result and then multiply by an extra z, this sort of hints to you it's induction. Now, one of the things you need to know how to do is prove de Moivre's theorem via induction, but only for integer values of n, of course. Okay, so the proof is written here, and we'll just quickly scan it. It looks a lot longer than it has to be, actually, but you should try writing this out by yourself. I think there's really only 5 main steps to be aware of. Okay, so first up, remember with induction, you write your conjecture, so this line here. Okay, so they're writing P for the proof that you're trying to figure out. So Pn, put a colon, then you write the left-hand side and the right-hand side. We're saying that the complex number, in polar form by the way, raised to the n, is really just the modulus raised to the n, cis, and then n multiple of the argument for all positive integers of n. Then we check the first case, okay? So that was step 1, this is step 2, to write the test case. Now n equals 1 is the first one. When we substitute n equals 1 on the left-hand side, you just have that expression as it is. Now if you use the right-hand side expression, we're putting n where you see it, then you literally get the same thing on both sides. So therefore P1 is true. Okay, third step. Remember, third step, we need to write an assumption phrase. Okay, now I would criticize this working here in this textbook. They need to write the word assume. Okay, so just remember for your working, and I'm going to deliberately write this. Okay, just to make it a point. All right. Assume PK is true. And in fact, that's all you need to write. They can write the actual statement. So if you wish, you can also write this just to have this in front of you. But it's not too hard to look at the previous result at the beginning and just pretend there's a K there. But it's useful to have it there, okay? So that's the third step, right? Then the fourth part now is to do the K plus 1. So you just literally start with P of K plus 1. I actually have to write this in as well. For me, I would have written here P K plus 1. Okay, as a subscript there. And colon, just turn that back up to normal. Right, so I'm starting this process here. Then on the left-hand side, you will get this. The idea is with brackets, you should always split them into the K and then multiply by the extra one. Because then now you can use the assumed information from above. So this is the right-hand side. You're going to substitute it right there. Okay, so you can see this is the line right here now. Then we know things about multiplying complex numbers. Okay, so we're allowed to use that result because that's already been established. So, but when you multiply the modulus. So that's why you can see the z is raised to the k plus 1. And then over here, the arguments are added. And then they factorize by theta. So you now see you've got k plus 1 lots of theta. And this is literally the right-hand side of de Moivre's theorem, where you're substituting k plus 1 as for the n. So now you can conclude equals the right-hand side. And then the final step, that's the fifth step. So I did tell you there were 5 steps. Okay, so you write your concluding sentence. And I've been asking you to recite this like a chart, okay, that you just have to remember it. Since the P1 was true, and I would say since what P1 is true, therefore PK plus 1 is true if pk is true, therefore pn is all true for all n positive integers. Then they extended this proof to have a look at negative n as well. So that means the theorem also works for all integers overall. And then finally they look at how to deal with it if it's a rational number. Okay, so you don't need to know how to do this second part and the third part, but you do need to know how to prove it for all n equals positive integers. Alright, so we've looked at de Moivre's theorem, what it is, look at this proof here. Finally, let's have a quick look at how to use it. So you can see in this example here, you've got the Cartesian form. So remember, de Moivre's theorem can't be used in Cartesian form, it has to be in polar form, right? So to multiply this to the power of, raise it to the power of 8, what you'll need to do is first convert this into polar form. Now I'm going to write this down. You can see the working here shown. The final result here is negative 128 minus 128 root 3i. And you can see they've used some unit circles here. I'm going to show you this by my own writing. So I'm just going to flick over here. So we've got root 3 plus I, all raised to the 8. Okay, so firstly, we need to convert this to polar form. So what I would suggest you do is you just draw a little sketch. Okay, and then you mark in where root 3 plus I is. So root 3 I. Okay, so you get a little right angle triangle. Hopefully you can identify that's the root 3, 1, 2 right angle triangle. So this is 30 degrees, which is known as pi on 6. Okay, so that hypotenuse there is 2. So the modulus is 2 cis pi on 6. That has to be raised to the 8. Okay, so now we know de Moivre's theorem. De Moivre's theorem says if z equals r cis theta. Okay, so I'm using the modulus symbol r instead of modulus z. Then z to the n equals r to the n cis n theta. Okay, for n, in fact, rational values, but I usually just write integers. Okay, so this is the theorem, but you can have it shown to you from the formula booklet if you really need to look at it. So it's easy. So the answer is 2 to the 8, and then cis 8 pi on 6, and then we'll simplify it. So 2 to the 8, 256, and then this is cis 4 pi on 3. Cool. So the answer, if you look at it on the Argand diagram, which I'll just draw this in again, 4 pi on 3, that means it's past 180. It's about here, isn't it? Pi on 3. I'm just trying to think here. We've got another third. Okay, so this angle here is 4 pi on 3. And this length here is quite long, so the modulus needs to be 256. So I can't really draw that to scale to do it justice. Now, if I want to, I can convert this. Okay, so this is polar form. I can convert this to Cartesian form. So let's have a quick look at how to do that, because you might be asked to write your answer in different forms. So just expand it. So you've got 256 cos 4 pi on 3 plus I sine I times 256 sine 4 pi on 3. Okay, and then we work out what the cos of 4 pi on 3 is the same as pi on 3. Okay, C-A-S-T. It's going to be negative. Cos of pi on 3 is 1/2. But it's going to be negative, so times negative 1/2. And then plus I times 256. And then sine of pi on 3 is root 3 on 2, but it's also negative. Okay, so overall, this turns out to be negative 128 minus 128 root 3 I. Okay, so that's our Cartesian form. And it looks about right because we've got a negative real part and a negative imaginary part. So remember, this is the real axis, this is the imaginary axis. So yeah, it's in the correct quadrant. Okay, so that's how you apply de Moivre's theorem when it's in polar form. Okay, we'll take one more look at an example. Okay, so you can use de Moivre's theorem in Euler form, which is quite easy to work out also. Just going to see if I can show you. No, well, actually, we'll just do it ourselves. So one last example over here. Okay, so you want to raise, this is an easy one, z equals 4e to the I pi on 5. Okay, so this angle is not a common one, but it's okay. You can still do it. So let's say you want to work out the 5th power, z to the 5. So that would equal all of this to the power of 5. Now what's great about it is you can just use your ideas of index laws. So this coefficient needs to be raised to the 5, and this part here gets raised to the 5, which is multiplication. Remember, a to the m raised to the power of n is a to the m times n. Okay, and all you've got is an extra number in the front. Okay, so you've got a k, so you've got k to the n, okay, there as well. Alright, so this will become an I, and this will just be pi. Okay, 4 to the power of 5 is the same as 2 to the power of 10, so it's 1024 e to the I pi. So this is in the Euler form, but we can convert it. So if you want to, you can write it as 1024 cis pi. So this is polar form. And finally, hopefully you can see this angle is actually quite a nice one. It'll be more simple to write it in Cartesian form. Pi is 180 degrees. So that means it's purely real. It's on the negative part. The answer is just negative 1024 in Cartesian form. There's no imaginary part at all. How do I know this so quickly? Okay, so what I'm doing is I'm imagining where it goes on the complex plane, okay? Because if it's pi, that means the angle there must be 180 degrees. That means your line must go here with a length of 1024. It's purely real. There's no imaginary part. Alright. So de Moivre's theorem is quite a useful property to know, and it's for powers of complex numbers. we will look at using this to do some further proofs, but please do the exercise so that you can get more practice with using de Moivre's theorem.